With that, let's give Daryl Oster a big round of applause.
Thank you. I think it's working. Thank you, Tom. I am very impressed with the DaVinci Institute and the openness that they have for entrepreneurs and just loads of interesting people and lots of value in being a member here. And I encourage any of you that aren't members to get with Tom and check out the membership here, because it really is a very valuable resource. How many understand this slide already? Well, lots of you do, okay. Perpetual motion is proven in nature, and I know there's a lot of people that will nitpick at that. There's some evidence that orbital velocities are decaying. There's other evidence that suggests that they might be increasing, and it kind of looks like with the expansion of the universe that orbital velocities might actually be increasing, and the motion in likelihood might be perpetual. So, you know, there's going to be crashes. All motion of the heavenly bodies is not perpetual. There's a lot of evidence that, you know, suggests that there might have been other planets around, or not planets, but moons around Saturn that made the rings. So, the average person travels 275 billion miles through space during their lifetime, because the Earth is orbiting the Sun at 67,000 miles an hour. The Sun is orbiting the Milky Way at 200,000 miles an hour. Part of the time the Earth's velocity adds to the Sun's velocity around the Milky Way, part of the time it subtracts from it. So we accelerate from about 133,000 miles an hour up to 267,000 miles an hour once a year without even really recognizing it. 275 billion miles per lifetime without using a single drop of gasoline. So what we're doing, our vision, is bringing space travel conditions down to Earth. The vision is being able to go from, this is a polar view of the world, Florida, we're here in Colorado somewhere, but a person could get from New York up across Canada, across Alaska, across the Bering Strait, across Siberia to Beijing, China in 2 hours at 1/10 of the cost of flying. Or products could move from any manufacturer in India or any manufacturer in China up across the Bering Strait to any Walmart in the United States in 4 hours or less. A pallet at a time minimum order instead of a shipping container at a time minimum order. And at about 1/10 of the cost. Before you stop and say it's a far-fetched idea, recognize that they are doing it in China. They are building evacuated tube transport in China. We lived there for 5 months. The first trip was in the winter of 2002, 2003, and the Chinese have developed a new form of magnetic levitation. It's called HTSM. And how evacuated tube transport works is eliminating almost all of the friction associated with transportation. When you're driving down the road in a car at 70 miles an hour, about 3/4 of the resistance is aerodynamic and about 25% of the resistance is rolling resistance. The rolling resistance can be eliminated with magnetic levitation, and the aerodynamic resistance can be eliminated by bringing space travel conditions down to Earth.
I believe that this nation should commit itself to achieving the goal before this decade is out of landing a man on the moon and returning him safely to the Earth.
The bold move of putting mankind on the moon created vast wealth and prosperity for the United States. U.S. intellectual property value now exceeds our tangible asset worth. Although manufacturing is shifting to Asia, half of global IP licensing income flows to the U.S. Evacuated tube transport is efficiency-improving technology that has benefits far exceeding what NASA created during the 1960s and 70s. Because of exorbitant costs, only a few astronauts ever experienced frictionless travel in orbit. By contrast, ETT will offer an enormous benefit of frictionless space travel on Earth for everyone to enjoy at any time. The value of ETT will dwarf the wealth that NASA-inspired IP and hardware created. The first nations to leverage ETT will trigger and ride a wave of unprecedented global prosperity. ETT will eliminate oil reliance, enhance global security, green the Earth, invigorate stagnant industries, and net millions of high-paying jobs. Most importantly, ETT will stimulate the global economy by availing an extremely high return on investments for companies who build it. ETT is a patented technology where travel occurs without air resistance or rolling resistance. ETT can accomplish 50 times more transportation per kilowatt hour than electric cars or trains. ETT is silent, ultra-safe, faster than jets, and is powered by electricity. Air is permanently removed from two 5-foot diameter tubes built along a travel route. ETT is not pneumatic tube transport commonly used to drive up banks. Car-sized passenger or cargo capsules travel in the tubes on frictionless magnetic levitation. Airlocks at stations allow transfer without admitting air. Linear motors safely accelerate the capsules. For most of the trip, they coast through the vacuum without using any additional energy. Acceleration energy is recovered at the end of the trip by using linear generators to decelerate the capsules. ETT will eventually serve most homes. ETT is networked like freeways. The capsules are automatically routed like internet traffic, yet a capsule can exit the system at any desired branch. Speeds of 350 miles per hour for in-state use will develop to 4,000 miles per hour for cross-country. That means New York to LA in 45 minutes, or New York to Beijing, China in just 2 hours. Empty ETT capsules weigh 400 pounds, yet can accommodate 6 people or 3 pallets of cargo. Guideways to support ETT capsules require 1/20th the material needed to support trains. Material efficiency and automated production will drop cost to less than 1/10 that of a high-speed rail, or 1/4 as much as a freeway. Automated switching allows 350 mile-per-hour ETT routes to exceed the capacity of a 32-lane freeway. ETT value will produce ROI high enough to guarantee private investment. ETT benefits will compound for generations. Collectively, companies have invested billions developing ETT, though most are yet unaware of it. For instance, many companies currently produce the hardware and software necessary to build and automate ETT. The technology is owned by ET3.com Incorporated, an open and growing consortium of licensees. These companies and individuals collectively network and leverage their assets to implement, manage, and improve ETT. Private investment of $500 billion in optimally placed ETT routes will displace up to half of U.S. transportation. The manifold annual return on this investment will include a direct savings of $1.4 trillion, time savings of $625 billion, environmental benefits over $200 billion, security benefits of $70 billion, and 20,000 lives saved annually from automobile accidents. This totals almost $2.3 trillion per year. Secondary benefits include economic expansion, better distribution of commodities, improved global standard of living, real estate value appreciation, and accessibility to education and markets, to mention only a few. Building a 14,500-mile ETT backbone from New York to London via Alaska, China, India, and Europe for less than $1 trillion would capture 10% of the $8.5 trillion global transportation pie by connecting major population and production centers. Traveling from New York City to Beijing in 2 hours on ETT with a comparable fare to flying would yield 90% profit margin. This allows greatly reduced transportation cost. China recognizes the immense value of ETT and holds a 5-year advantage over the U.S. in its implementation. Instead of waiting for others, we have a patriotic duty to leverage our advantage on intellectual property and be the first nation to commercialize ETT. We can boldly create unprecedented environmental, social, and economic returns through ETT. This will usher in an age of global prosperity for many generations. The United States will enjoy enormous profits by providing transportation, just like Saudi Arabia sells oil. Find out more and get involved in creating the shift to ETT at www.et3.com. Thanks for watching.
And so, my fellow Americans, ask not what your country can do for you, ask what you can do for your country. My fellow citizens of the world, ask not what America will do for you, but what together we can do for the freedom of man.
Evacuated tube transport can be built a lot cheaper than elevated high-speed rail or roads. The main reason is if you have a vehicle that only weighs 400 pounds, yet can carry the same 800-pound payload as a typical car, you only have 1,200 pounds of live load. Compare that to a 100-ton locomotive, 200-ton locomotives passing on a bridge span. It takes 35 times more materials to build elevated high-speed rail as it does to build evacuated tube transport. Or if you compare that to 40-ton trucks on a interstate freeway bridge, bumper to bumper across 4 lanes. Huge amount of live load compared to the infrastructure for evacuated tube transport. And in the case of trains, because trains are limited by a physical moving switch, the frequency of vehicles that can use that very expensive infrastructure is limited to 1 vehicle every 5 or 6 minutes. So with evacuated tube transport, it uses a freeway philosophy where the vehicles control the switching in the network instead of the infrastructure controlling the switching. So the infrastructure, the guideway, the tubes do not limit the frequency of vehicles that can use the system. So since it's automated, we can achieve much, much higher capacities, just like automation has done for telecommunications. Could you imagine if the cell phone traffic and the internet traffic that takes place in the world today were routed by human switchboard operators that had to actually physically switch every single call? How much labor would that take? How many drop calls would we get? We're getting drop calls all the time on the freeway and on highways. The transportation equivalent of drop calls. 40,000 people die in transportation-related fatalities every year in the United States alone. Most of those are preventable. They fall under 2 major classes: failure to control the vehicle and failure to control the pathway and the conditions of travel. Evacuated tube transport substantially eliminates most of the reasons that people die in transportation-related fatalities. We can achieve much higher reliability in transportation through automation, just like we have in communications. ET3 compares to one 5-foot diameter tube at a design speed of 350 miles an hour can accommodate 20 lanes of freeway traffic. So a 2-way system is the equivalent of a 40-lane freeway. That's at a design speed of 350 miles an hour. At 350 miles, and that's only using 1/3 of the theoretical capacity of the tube. At a design speed of 350 miles an hour, that's 519 feet per second. If we only use 1/3 the theoretical capacity and the vehicles are 16 feet long, the nose of one vehicle to the nose of the next vehicle, 50 feet, that's 10 vehicles per second. Now if you double the speed, you still have 10 vehicles per second, but now you're moving at 1,000 feet per second. So you divide that out and you have 100-foot spacing between each vehicles. So now every time you double the speed, you can merge those 2 lanes together just like a zipper going together, and you've got twice the capacity. The capacity scales with the design velocity. So at 4,000 miles an hour, it's over 100 vehicles per second capacity. A single pair of 5-foot diameter tubes going across the Bering Strait could carry every single pallet on every single container in every single container ship going between China and the United States. The capacity of ET3 is phenomenal. It takes a lot of airlocks to exploit the capacity, but ET3 is granular compared to rail that needs a Grand Central Station and a bunch of people funneled together to justify that huge capital expenditure. ET3, on the other hand, is more like a freeway philosophy where the exits in the system can be added according to demand, just like exits on a freeway. So it's much more granular, about 10 times the granularity of high-speed rail. ET3 is an open consortium that anybody can get involved with and leverage whatever skills that they have, whatever production assets that they have, whatever intellectual properties that they have that can help bring ET3 to fruition quicker. In Henry Ford's day, he had to aggregate what would now be billions of dollars to build the capacity to build everything, because none of the capacity existed to build cars before Henry Ford. Everything was built by hand. So he had to bring together what would be billions of dollars to build the capacity to make enough steel, to build the capacity to build engines and transmissions and gears and bearings and all the things that we take for granted now that are already produced by hundreds, maybe even thousands of manufacturers all over the world, have already collectively invested billions of dollars in the production capacity for ET3. So we've adopted an open consortium model where those manufacturers and individuals, experts, can leverage their past investments in intellectual property or production capacity to help create a new market for those assets that might be 10 times bigger or 100 times bigger than the present markets that they're serving. So evacuated tube transport can get the world economy going again, get those companies that are maybe only working 3 or 4 shifts a week right now, barely hanging on. If they could create a new market for that production capacity, they might be able to keep those machines going, keep that investment going 3 shifts a day, 7 days a week, and still not keep up with the capacity. So they could sublicense their competitors under substantially identical terms and earn a commission on any revenue, royalty revenue that they generate for ET3. A manufacturer who joins the ET3 consortium pays a 6% value-added royalty to ET3 when they produce parts for ET3. For instance, if a vacuum pump from a vacuum pump manufacturer that's necessary for ET3 operation, maybe, let's say it costs $1,000. So that manufacturer, if it's going into an ET3 system for ET3 order, if he marked it up $60, the end consumer ends up paying that 6% value-added royalty for them, and they've helped to create a new market for their production capacity that might be 100 times bigger than the present markets for vacuum pumps. So the open consortium philosophy is a very low barrier to entry, and there's a lot of experts that are leveraging their intellectual property. Also, the company is owned by the licensees. The licensees contract with ET3 to perform all management services, and for instance, our bean counter and chief financial officer is a CPA that ordinarily makes $200 an hour selling his bean counting services. At the end of the year, he takes a couple hours to provide services to ET3, and we compensated him with shares of ownership in the company for the value that we agree that he is providing. The website people, same way. So literally any skill or intellectual property can be leveraged to help create a new market that is potentially the biggest market in the world. $8.65 trillion is spent annually on transportation on a global basis. ET3 can displace approximately 90% of that $8.65 trillion that's spent on transportation. There are 5 patents in the intellectual property portfolio. Now it's grown from the initial patent in September of '99, and we have several more patents that we intend to file shortly. Any licensee can also leverage their intellectual property and intellectual capacities to help make improvements to ET3 and sublicense those improvements to ET3. So if their technology is used to build a system and adds value to the system, they will receive a portion of that royalty. Half of that royalty goes to the technology holders of that 6% value-added royalty. So If a company comes up with patents to make tubes much more cost effectively than present manufacturing capacity, and 80% of the cost of the system is the tube cost, 80% of that 6% royalty is how much? Anybody have an idea? Close to 5%, not quite, 4.8, somewhere in there. So half of that would go to them as other people use that technology, and they've helped create a new market for their intellectual property, just like manufacturers can help create a new market for their production capacity. If they make that improvement, they own 100% outside of ET3. So if their pipeline making capacity can make oil pipelines or gas pipelines or other pipelines better, they own 100% of that, and none of that royalty goes to ET3. So it's a new market for using a blue ocean strategy instead of a red ocean strategy. What we are in a kind of a catch-22 situation, or a chicken and the egg situation. We have financiers that tell us that they've demonstrated a capacity to raise up to $600 million for infrastructure projects in the past. The two things that they need to proceed for raising money from ET3 is a guarantee that the government's going to permit it, permitting and right-of-way issues and those types of things. And they also need a neutral third-party feasibility study that shows that the demand is there and that ET3 can meet that demand and those types of things. The government officials are not real excited about permitting something that hasn't been demonstrated. So it's kind of a catch-22 situation. So we really need to demonstrate the viability of ET3. To start out in baby steps, it's going to take an investment of about $10 million to build a 3-mile single tube system. It takes about a mile to accelerate up to 350 miles an hour, and then the vehicle would coast for a mile. During that time that it's coasting, it would switch in and move over slightly to prove that the high-speed switching works, and then converge back, and then 1 mile deceleration phase. We believe that that could be built at a theme park and actually be a revenue producer and produce a favorable return on investment for that $10 million. So if anybody knows people at Disney or Magic Mountain or any of these amusement parks, those are contacts that people could leverage. And if you sub-license those and they decide to make those types of investments, you would receive a 5% commission on any royalty income that they generate for ET3. What's 6% of 10 million? Okay, 600,000, and a 5% commission on that, 30,000, is that right? So better than a poke in the eye with a sharp stick. But when we start talking about billion-dollar systems, that 5% commission turns into $3 million. So it's incentive to grow the company and bring more people involved with the consortium. I should have repeated the question. The question was, will the Chinese initial experiments that have been done in China satisfy the U.S. government? And I think it should, but so far it's not.
I think you actually met before. It's Kevin Lauer.
Oh, is this working? Oh, I guess it is.
So what actually has been done in China? Have they actually done this, what is it, three miles or something like that?
This is the high-temperature superconductor Maglev. This is the prototype HTSM vehicle built in China. And that's Brenda and I getting a little ride. It levitates about 1 inch high, and this is how it works. A piece of yttrium barium copper oxide superconductor is brought down to liquid nitrogen temperature. There's some cotton or gauze surrounding that little puck there. And you can see it levitates in the presence of a magnetic field. It's substantially no resistance in the linear direction. In the vertical and horizontal direction, there's resistance in both directions. You can hang it upside down and the vehicles will hang upside down from it. It's totally stable without any electricity or electronics, and its coefficient of friction has been measured as low as 10 to the negative 7. If that vehicle weighed 1,000,000 pounds, the drag force would be between 1/10 of a pound and a pound. And then linear electric motors, of course, accelerate the vehicle up to speed. So the Chinese have developed this HTSM technology. It will support about 80 newtons per square centimeter of mass at a levitation height of about 3/4 of an inch on that prototype. Now that prototype vehicle that you saw Brenda and I riding in China will consume about $3.50 worth of liquid nitrogen, will keep that vehicle levitated for roughly 7 hours. In an evacuated environment, the heat gain is reduced. Does anybody know why?
There's no conductivity through the air.
There's no conductivity through the air, right. There's no convection of thermal conductivity. So we believe that we can reduce that 50 cents an hour cooling cost down to about 5 cents an hour cooling cost for ET3. So the cooling cost is trivial it'll take more electrical energy to accelerate the vehicle up to speed. About $25 worth of electrical energy will accelerate a car-sized capsule up to 4,000 miles an hour. It takes about 103 miles. And then the vehicle coasts for the entire trip using hardly any additional energy. When it arrives at the destination, as much as 90% of that energy can be recovered when the vehicle slows back down with a linear generator. Just like a Toyota Prius, when you step on the brakes, that electrical energy is regenerated and goes back into the battery. So in the case of ET3, when the vehicle slows down, about 90% of that electrical energy can be recovered and used in the power grid to either accelerate capsules back the other direction or for other uses.
So Daryl, let me ask you this question. It seems like the human element is always the piece that slows everything down. So when you're actually getting people into a tube, going through security, and make sure they got all their stuff with them, their purse and everything. They need to comb their hair right and everything so that they can get into the tube. It all takes a lot of time. And so as you're queuing people up to get into one of these cars, can you kind of step us through what that process would be like and then how that tube then gets loaded into the bigger tube?
Sure. Yeah, it takes about, let's get that little, I've got a little animation here that shows how that works. The airlock. You just saw a capsule enter the tube. In the lower airlock chamber, it's exchanging with the upper chamber so it can accept the inbound capsule because it's evacuated. When the capsule goes into the lower chamber here, it displaces almost all of the air that's in there. And then the two gate valves close. When the two gate valves open, it can go into the tube without letting any air in. So the capsule itself does most of the work of evacuating the chamber. Now, what you'll do is when you drive up to the, like say a Walmart store, about 90% of the population of the United States is within 15 minutes of a Walmart store. So that's kind of our target for the initial, profitable implementation can disperse access portals with about the frequency of a Walmart store, about 1 per 20,000 population or so. So the experience would be you park your car at the Walmart, you drive across or you walk across their store and you buy the last minute things that you need. So Walmart's very happy to have the airlock at their store so they can bring product in at much lower cost and much less time from manufacturers in China and India. And then all these people walking across their store to use the access is going to increase their revenues, and they can charge them to access the portal. So what you'll see is you'll see a moving walkway that you step onto, and a capsule will be right there moving exactly the same speed now that you are. Just like the Disney mechanisms. Who's been to Disneyland? Those have about a 15-second queuing time to queue people in and out in a continuous process. So the vehicles wait for the people instead of the people waiting for the vehicles. It's not like at an airport where you have to aggregate, 200 to 400 people to make that air flight efficient. The vehicles are car-sized vehicles and leave with more like the frequency that people walk through the door. So you'll walk through the door, you'll go through a scanner that can sniff for explosives and all those types of things. And there'll be a pre-screening process with biometrics that streamline that process much more effectively and weed out the high-risk types of people that might want to cause harm to the system. So you move through there, you move onto the walkway, and you carry your own stuff and you put it in a capsule that's for cargo, or behind the seats in a capsule, in a special cargo area in the capsule. And you sit down in your seat, and then the vehicle goes through the airlock. It takes about 20 seconds to get into the system, and then about 26 seconds to get out of the system. 26 seconds on both the in and out. So it takes about a minute of time overhead. So for a 5-mile trip, it doesn't really make sense for ET3 because of that 1 minute time overhead, and there's energy overhead for providing the breathable air and those types of things. I don't know if I fully answered your question, but I hope people have a little bit of an idea.
What's the minimum distance that's reasonable to travel?
About 5 miles is where you're break even on a energy standpoint and break even on a time standpoint.
Okay.
So more like a freeway.
Jack Panter, I'm a licensee with ET3. If I could add something, Daryl, is that everybody hates going through security at the airport. That's only one place you can go through there. We can have portals all over the city, actually. So whatever crowd you see at the airport, we're going to have at least 20 portals that you can hop into the tube system. And I'd like to also, somebody asked about the cost of energy. I used to be an airline pilot and flying long transpacts and transatlantic flights. It was kind of interesting to me at the time to fly from, say, Seattle to Tokyo. It's 10 hours at 25,000 pounds an hour, and all this works out to be 250,000 pounds of fuel to go from Seattle to Tokyo. And it's about the same whether anybody gets on that plane or not. So the amount of energy is to run the machine. The same applies to your car. If you get in your car and drive from Denver to Omaha, if you don't even get in the car will consume the same amount of fuel as if you're in the car. We spend a lot of our energy just running the machine. The same will happen with high-speed rail. If they have a high-speed rail in San Francisco to go into Los Angeles, which probably most people won't use, it's still going to cost the same amount of energy to get it there. Full or empty, it won't matter. In this particular system, the capsule doesn't even go unless you want to go closer to what your car does. Anyhow, if that
Thanks,
answers.
good points. Did I understand the question right? Is it what happens if something happens to the system, like say an asteroid crashes into one of the tubes or something, or a 747? Yeah, that's a very good question. Now, ordinarily, that would be a lot of risk. Obviously, if there's a capsule right there, the people are going to get wiped out. Just like if they're on a car on a freeway and an asteroid hits the freeway, people are going to get wiped out. So, what happens to the flow of vehicles in the system? Is that your question? Okay. In the case of a very unlikely event like that, what would happen is the sensors in the tube would sense that air is rushing into the system at close to the speed of sound, and simultaneously along that entire branch that cannot be isolated from the rest of the system and traffic diverted around that particular problem, for that particular branch, the entire system will be flooded with air through apertures that are situated and spaced along the length such that the airflow going in through those valves is admitted at such a rate that it slows the capsules down at a fast survivable rate and aerodynamically brakes the vehicles. And also that will provide a cushion of air between those vehicles to cushion any potential for collisions. It'd be like a giant airbag, several hundred feet long between each capsule. So I don't know if that answers your question or not.
People that trapped in there?
Okay, so the question is now, are the people trapped in there for some time? Yes. Just like, but it's far better to be trapped in a very benign and comfortable environment than to have your wings fall off your airplane at 30,000 feet. People can, cut the tube open with a carbide tip chainsaw. The emergency people get there, or the vehicles could be propelled with moving air pressure through the system to get the people out. But those events, compared to the problems that we experience in transportation now, the important thing to realize is all the cataclysmic events that we're afraid of, that we get whacked out and overly fearful about, like acts of terrorism and tsunamis and mudslides and tornadoes and hurricanes. If we add up all of the fatalities that occur from those random acts of God and acts of terrorism, it constitutes less than 1% of transportation-related fatalities. We think it's a lot better to focus on what's killing 99% of the people instead of what's killing 1% of the people. And I believe that the things that are killing 1% of the people will be reduced substantially with evacuated tube transport also.
So, my name's Sherry. My question is about the fear piece aside, about what about just from a practical point of view, when you have thousands of miles across the Pacific, for example, to China, the appeal of that, just simply practical appeal of that as far as terrorism, and the inability to police that stretch. It just seems like it would be a neon light flashing, going, boy, you could mess up a whole lot in the world finding that line.
Yeah, well, fortunately, most people are not bent on terrorism. And, while it's true, any mode of transportation is subject to acts of terrorism. And we're kind of overly emotional about that right now. As far as the logistics of patrolling that, a lot of that can be done electronically. And the security sensors, also the high-speed global backbone, the more sensitive high appeal targets will be substantially underground. And the location of that is going to be hard to determine for somebody engaged in random acts of terrorism. It'll be far underground, under rock, and the cheapest place to cross the ocean is the Bering Strait. And that would probably be the most prone to a security interruption. Extra security measures in that location would be prudent, but it's a pretty inhospitable environment, and not a lot of people up there anyway, and if somebody's up there, they better have a good reason for it. So,
right-of-way issues. No overall cost of the system. The construction part is one factor, but somehow getting the right-of-way, people don't want you to go over their land, or they do want you to go there. Have you factored in those costs, and how's that handled?
Those costs can be pretty high when going through cities. But if we compare with other transportation modes, which those issues must be solved with any transportation mode, the transportation flux that's possible with ET3 is orders of magnitude improved. So the relative cost of the right-of-way per capacity is also reduced. And the existing right-of-way can be used for many, many purposes with ET3. It's not like a freeway where you have to worry about keeping animals and kids and other vehicles, errant vehicles, out of the path of travel. With evacuated tube transport, if it's above ground, it'll be elevated above the ground so people can still farm the right-of-way underneath it. So that will ease a lot of those issues. They can go through neighborhoods a lot less obtrusively. One of the biggest problems with transportation right-of-way is that everybody wants to use transportation, but nobody wants a freeway or a airport in their backyard. And you can't blame them, mostly because of what? Noise is the big reason. The horrific noise from that. Evacuated tube transport will be virtually silent, which will minimize a lot of those NIMBY issues. And have you heard of there's the NIMBYs, and then there's also the cave people. Have you heard of the cave people?
No.
Citizens against virtually everything. So we think there will be tremendous opportunity in stakeholders that already own huge amounts of right-of-way in the United States. There's roughly 200,000 miles of power line right-of-way in the United States that cannot be used for freeways because if a truck runs off the freeway and takes out one of those towers, you got 50 million volts dancing on the road. So with evacuated tube transport, a lot of those existing right-of-ways might be able to be used, and a lot of them are very straight. So we think also existing railway right-of-ways. Railway reached its peak in the United States in 1916, where there was 270,000 miles of active railway right-of-way in the United States. Right now, less than 130,000 miles of that 270 is in use. So about 140,000 miles of unused railway right-of-way, some of that, there's chances could be leveraged for evacuated tube transport. On the subject of right-of-way, there's about 2 million miles of paved roads in the United States. A lot of those freeways could be used for evacuated tube transport right down the median or off to the side or underneath. So there's lots and lots of right-of-ways. There are about 50,000 miles of that 2 million miles is the interstate highway system. And that 2% carries 60% of the ton miles of road travel and the passenger miles of road travel. So similar will be with evacuated tube transport. Since the capacity is so much greater, the capacity of one 5-foot diameter tube at 350 miles an hour is the same as a 40-lane freeway. So to provide the same coverage as the interstate highway system, we might need only 30,000 miles instead of 50,000 miles of freeway in the United States.
Having had physics in high school, this thought came to my mind. What is the distance between, I don't like capsules, but between motor cars, between the units? What is the distance at 350 miles an hour? What is the minimum distance you can have between them, let's say? I'm just building up to. So
Yeah.
what, 100 feet, 100 yards?
If we only use 1/3 of the theoretical capacity, which is the position with automated means, by the time that vehicle's traveled an inch, even at 4,000 miles an hour, computers can make thousands or millions of decisions. So the positioning accuracy is within an inch easily. If we have a capsule that is 5 meters long, 16.4 feet long, and we only use 1/3 of the theoretical capacity, let's add a few inches to that and make it 16.66 feet long, and we're only using 1/3 of the capacity, that means 50-foot spacing between one capsule to the nose of the next capsule would allow 2 capsules in the case of an emergency to merge in between any 2 in the system. So if we say that we're only going to use 1/3 of the theoretical capacity of the system, so in case there is an emergency somewhere, that stream of traffic can be routed into another somewhere in the network. So it also provides reserve capacity for other emergencies too. So at a 50-foot spacing and moving 500 feet per second, that's 10 vehicles per second capacity at 350 miles an hour. That's 220,000 passengers per hour. That's 10 times the carrying capacity of a heavy rail system. of a high-speed rail system.
Yeah, now, you just built into my problem for physics. If you are going to switch this guy to Walmart, and this guy's going to LA, assumedly,
Mhm.
or anywhere, now I'm looking at the mechanical factor of the switch
Mhm.
with something.
It's not a mechanical switch. It's like a freeway.
50 miles an hour.
It's not a mechanical switch. It's not like a railway philosophy. The vehicles control the switching. The guideway is completely passive, just like a freeway. A freeway, the ideal situation, this is a freeway philosophy. It's not a train system. It's much more like a car on a freeway, where the vehicle accelerates up to speed before it merges into the traffic. It reaches that exact design speed and then merges into that slot that's already been reserved for it. From origin to destination for the entire trip, that trip has been planned. Now, that capacity, the people in that vehicle can, just like in a car, make a decision that they want to stop halfway, get off at the next exit if they have to use the restroom or something. They hit the button, and it recalculates their plan. If there is capacity available at the next station, then they can be rerouted.
Okay, so finally then I'm trying to picture it. I'm picturing all these straight tubes, so the tubes are going to be forking all the time.
Most of the guideway will not be at the 4,000 mile an hour design speeds. There's let me bring up a slide here that will answer some of your questions regarding that, I think. Can everybody see this? What this is here is, this is the first column here is design speed, mile per hour in column B. So if we're looking at a design speed of 350 miles an hour, let's say line 23, the time that it takes to get up to that speed is 16 seconds. You've traveled 1,190 meters, 7/10 of a mile to accelerate up to that speed. Let's call it a mile because it's 350 miles an hour instead of 342 miles an hour. And that's the minimum curve radius, is about 1.5 mile minimum curve radius. This is the passenger capacity in passengers per hour, or the ton per hour of cargo. This is the amount of energy compared to a 40,000 pound truck, about 1.8 kilowatt hours of electrical energy, kinetic energy in the capsule. Now if we go up here to, so that's about 2 cents worth of electrical energy, or 20 cents worth of electrical energy at retail, 10 cents a kilowatt hour. If we go up here to 4,000 miles an hour, then we're looking at 103 miles to accelerate up to that speed. So if we look at a freeway situation, most of the infrastructure, paved roads in the United States are not freeways. They happen at slower speeds, the switching and everything that occurs. So it'll be the same thing with evacuated tube transport. Most of the guideway will be at design speeds of maybe 350 to 500 miles an hour. Where you're only looking at a mile to accelerate up to speed, merge into the flow of traffic, the minimum curve radius about 1.5 miles. So a lot of that can take place on existing freeway right-of-ways. Oh yeah. It's just like a freeway. Ideally, the freeway is a network. So the network means that it's all interconnected together, and a person, theoretically, once you merge into the flow of traffic, if that vehicle were automated, it takes you through the system at the design speed, 70 miles an hour the whole way that you're traveling. When you get to the destination, you merge off onto an off-ramp before the vehicle slows back down. Then it slows back down, that energy can be recovered, and you get out at the access portal.
All right, we're going to take a short break here. Let's give Daryl a big round of applause.